Okay, welcome all at our weekly seminar at Jagiellonian. Today, our speaker is Michał Seweryn. Michał is finishing off PhD these days. It's on combinatorics of partially ordered sets and its connections with minor theory. Hopefully, when it's all done and successfully defended, we're going to start a postdoc position later this year at ULB in Brussels, right?
Correct.
Yes, but today the topic of your talk is not within your thesis. It's an independent
Correct.
result, something in structural graph theory. We will see the details today. Welcome, the floor is yours.
Okay, thank you very much for having me. Yeah, this is a joint work with Piotr Micek, Rafael Steiner, and Sebastian Widegreff. So without further ado, let's move on to the topic of today's talk. So one of motivations for our research is a family of problems related to Erdős-Posha theorem. So Erdős-Posha theorem answers the question when a graph doesn't contain many disjoint cycles. So one very simple abstraction for a graph to not have many disjoint. Oh, one thing. Whenever I talk disjoint, I mean vertex disjoint throughout this talk. So one simple abstraction for a graph to not have many disjoint cycles is when it has a small set of vertices, so that after removing them, we are left with a forest. We can easily see that any cycle in the original graph must contain at least one of those vertices. So the maximal number of cycles in the graph is upper bounded by the number of the vertices we deleted. So it turns out that this, in some sense, is the only abstraction. Erdős-Posha theorem states that for every graph G contains either k vertex disjoint cycles or a small set, so a set S whose size is bounded in terms of k, such that there are no cycles in G minus S. So after removing those vertices, there are no cycles left. So it's a forest. And I'll just note that this function f of k, the optimal function f of k for this theorem is scale of k. This is a well-known result, and there are there's a lot of research answering this kind of question, where either we want to somehow understand the relation between the maximum number of some objects we can pack and a minimal size of a set which covers all objects of this type. So today we will be talking about some generalization of Erdős-Posha theorem, which originates from the fact that a cycle is nothing different than a subdivision of K3, the complete graph on the three vertices. So now, if we formulate it this way, we can easily consider a generalized version of Erdős-Posha and ask for our favorite graph, say K4. Is it true that either we can find K disjoint subdivisions of K4 or a small set of vertices such that after removing them, there will be no subdivision of K4 at all? So this motivates this definition. We will say that a graph H has the Erdős-Posha property if in any graph G, which doesn't contain K vertex disjoint subdivisions of H, you can always find a set of vertices bounded in terms of K, so that after removing them, there is no subdivision of H in our in the remaining graph. So Erdős-Posha theorem, using this terminology, says exactly that K3 has the Erdős-Posha property. So it's a natural question to ask, given this definition, which graphs have this Erdős-Posha property and which do not. And the answer is quite surprising. It turns out that it's very connected to topological properties of graphs. So in particular, if our graph H is not planar, then it doesn't have Erdős-Posar property. When the graph is planar, then it's a bit more complicated. And as if the maximum degree of our graph is at most 3, then this graph does have the Erdős-Posar property. And in the case where this maximum degree, like this is connected to the fact that whenever we have maximum degree at most 3, then being a minor is equivalent to being a topological minor. And in some variant of Erdős-Posar property, where instead of having subdivisions, we want to have some kind of expansions, which is like a operation reverse to taking minor, then this is exactly the boundary. It's planar no, and not planar if in this sense a graph has Erdős-Posar property if and only if it is planar. But in the case where we consider this topological minor version, so we have we want to have subdivisions, it gets pretty wild if we allow vertices of degree at least 4. There's a nasty characterization of this of graphs which have the Erdős-Posar property, and it's due to Liu, Posel, and Bolan. But they are it's quite complex, this characterization. In particular, it's NP hard to recognize graphs which have Erdős-Posar property. And what's interesting, there even exist trees which don't have the Erdős-Posar property. So it's quite surprising and counterintuitive. So I'll give a brief sketch of the proof why when H is not planar, then it doesn't have Erdős-Posar property, and why when you have subcubic degree, like subcubic planar graph, then it does have Erdős-Posar property.
So one can mention that this stays in a sharp contrast. Instead of subdivisions, you consider graph minors, because then the cut is very simple. It's just tonality itself. Right?
Yes, I mentioned that like.
Oh, sorry. Okay.
A minute ago.
I lost the train. Sorry.
So, but yeah, this is quite important. So it's worth emphasizing, and it shows how topological minors can be surprising. Okay, so let's see why when we have a graph H which is non-planar, so it cannot be drawn on a plane so that the edges do not cross, why in such case it doesn't have Erdős-Posar property. To prove that, we need to construct a graph which doesn't contain many disjoint subdivisions of H, but if we want to kill all subdivisions in the graph, we need to remove a lot of vertices. And the construction of such a graph G will be topological. So we will not dwell, like we will not go deep into topology. It would be just some sketch of the proof. So we can consider all orientable manifolds, sorry, all orientable surfaces of positive genus. So we have torus, double torus, triple torus, and so on. And we can consider the first one in which H can be embedded. So suppose that it's, for example, this double torus. And let us embed our graph H on this surface. And from this embedding, we will construct our graph G. We will thicken this graph by replacing each vertex by a gadget and each edge by a matching between two gadgets. So it will look something like that. Whenever we have some vertex V and some outgoing edges, we will replace it with, maybe I will just stay here and point with my mouse so that others can see. So this vertex V is replaced with a gadget, where in the middle of this gadget, there are many copies of V. Each of them will have the same degree as V. And they will be connected to this cylindrical grid, which has like a lot of connections and it's well connected. And on the boundary of this gadget, we will have consecutive parts of vertices, each corresponding to one edge. And each edge will be replaced with a matching with vertices having like being consecutive vertices on the outer face. And now I will not prove it rigorously, but you can see that if you want to, and if you will only remove small number of vertices from this graph G obtained by replacing vertices with those gadgets, you will still have some subdivision of H survive. So you will still have one of those black vertices, one of those copies of B will survive, and you will still be able to find the linkage, so the internally disjoint paths from that vertex to neighbors. So now it remains to argue why this resulting graph G doesn't have many disjoint subdivision of H. But this follows from this fact that if we consider one subdivision of, so observe first that this graph G, it can be embedded on the surface because we can transform the embedding of H into a embedding of G. And since that, we know that whenever we have some subdivision of H in our graph G, then it gives rise to some embedding of this subdivision in the surface. And since this is a minimal surface which contains our graph H, it will mean that it will split this surface into polygons. So whatever is disjoint from our subdivision will need to be contained in one of those polygonal faces, and therefore will be planar. So we will not be able to embed another copy of H. So we actually show that it already fails for k equal 2. We will not be able to embed, to find two disjoint copies of H in our graph G. Now we will move on to the case where we have a subcubic planar graph. So in this case, we will make use of grid-minor theorem. So by grid-minor theorem, we know that whenever we have some planar graph, then for a sufficiently large true width, we will always find this graph as a minor. And since we are dealing with a subcubic graph, we know that this is equivalent to containing disjoint subdivision. Sorry, it is equivalent to containing a subdivision of our graph H. So if our there exists a constant C, which is polynomial in the k times the number of vertices in H, such that if our true width is greater than that constant, then G contains k disjoint subdivisions of H. So we need to only assume the case where we are dealing with a graph of true width at most C. Now, I claim that if we have true width at most C, then unless we contain many subdivisions of our graph H, we can find a small set of vertices which hits all subdivisions of H. And the size of this small set will be, it will be a union of k times the number of components of H, but it's upper bounded by the number of vertices in H times C plus 1. So it will be a union of k times V of H bags of optimal tree decomposition. So suppose that we have true width at most C, and we have some decomposition of our graph. Then we can consider for each subdivision in our graph, we can look at its trace in the tree decomposition. So all nodes in which the bag contains at least one vertex of our subdivision. And we can choose a subdivision for which the highest node of this trace is as low as possible. So for example, suppose here we have one subdivision here, then we add this bag of this node to our set. Next, after removing S1, the lowest subdivision we have is here, then we add it to our set, and we have one more, and we add it to our set, and this way we obtain as like either this procedure continues for a long time and we find many subdivisions of our graph, or it terminates, in which case we hit all subdivisions of H, because if there was anything left, we would have taken it earlier. So there's one minor assumption that I made here, namely that the graph H is connected. And if so, under this assumption, we don't have this V of H factor, and this argument works. It gets a bit more complicated if our graph is disconnected, but it also can be done. But we have to pay extra factor times the number of components in H.
So when you take it back and you take it to leave it, so the property you have is that all the remaining copies are in this kind of root part of the composition. It's not hidden anywhere downstairs. Yeah, that's the.
Yes, correct. If I remove some node, then I know that no subdivision disjoint from this set is below. So this implies that when you have a planar graph which is subcubic, then it does have the Erdős-Prosser property, and this function is polynomial in K and the number of vertices in our graphs. I mean, this is not very important. Usually when we consider Erdős-Prosser property, it's more the qualitative properties are more important than quantitative, and the function is not as important. Many papers don't even mention what is the optimal function, but we will see why I emphasize it in a second. So now we will consider a variant of our of this Erdős-Prosser problem, where we add divisibility constraint. So we would like to not only we would like to consider only those subdivisions which have the property that whenever we have a path between two branch vertices, then it has length divisible by some integer m. And Thomassen showed that such subdivisions also have this kind of Erdős-Prosser property. So whenever you have a subcubic planar graph H and some number m, positive number m, then there exists a function such that for any graph G and number K, either G contains K disjoint subdivision of H, which has this property which I described earlier. So any path between two branch vertices has length divisible by m, or there exists a small numbers of vertices such that after removing them, we don't have a subdivision like that. And the proof of this theorem follows from almost everything that we've already seen. So we've seen why there's only one thing that we need to fix in our proof, which we had earlier to make it work. Namely, we need to somehow obtain a subdivision of many subdivisions of H, which are not only any subdivisions, but ones with paths divisible by m. And here, the just grid minor theorem alone doesn't help. We need to put some extra work. And therefore, it's convenient to consider a structure which is called a wall. So unlike what this title of this slide suggests, this is not a wall. This is a grid, a 4x8 grid. And in general, if you want to construct n wall, you start with an n by 2n grid. Next, what you do, you remove every odd horizontal, not horizontal, each odd vertical edge from each odd row, and each even vertical edge from every even row. This is pretty confusing, but I think that the figure explains it all. And we can see why it's called a wall, because the faces form a structure like bricks in a wall. And so we will denote such a wall by Wn. So for example, this is W4. And this is example of a wall, but in general, when we talk about n wall, we also allow the paths to be subdivided. Sorry, the edges of the W4 to be subdivided. So we can put extra vertices in the edges. And the walls are very, very important in structural graph theory because they are one kind of structure we always can find in graphs of large tree width, not only as minors but just as subgraph. We can obtain such a wall in a graph of sufficiently large tree width. We call those black vertices, which were like the edges of W4 before subdividing it, are the branch vertices. And
some people call them pegs.
Pegs.
Yeah,
Okay, so that's one way. I found myself that the terminology, like what people call some things, is quite inconsistent when it comes to walls. So I don't know, but yeah, that's one way. But I'll call them branch vertices here. So Thomason proved his version of Erdős-Mosha theorem with divisibility constraints by proving the following claim. For any integers n and m, there exists some g such that every g wall contains an n wall such that every path between two branch vertices has length divisible by m. So within a big wall, we want to find a smaller wall which has this nice property that whenever you have path between two branch vertices, it has length divisible by m. Note that the rows of the wall, our wall, don't need to be aligned with the rows of the original wall. So this can be completely different. And it's easy to see that our previous theorem follows from this observation, because if we can find a wall where the distance between any two branch vertices is divisible by m, then we can find our subcubic graph in our wall, and then each path will be with each edge will be represented by a union of those paths between consecutive branch vertices, and therefore we will have this property we want. So now we are ready to understand what is our work that we did with our co-authors. I did with my co-authors. So we were considering this function g and m and see if we can somehow find a good bound for the optimal bound. Like we wanted to ask how large must be original wall so that we can find the desired wall. And so here is the summary of our results. So we focus on the case where we are divisible by prime number p. So if we have some prime p, then in the case where p is odd, then this function g of np is linear in p times n. And if in the case where the prime is 2, then we don't have a linear bound, we have a bound of n log n. So yeah, this means that whenever we have we want to find a wall where where each path between two branch vertices is divisible by some odd prime p, then it suffices that we start with the wall of size roughly p times n. So this we can compose it to generate a bound for g and m. So where m is arbitrary number, not necessarily a prime. Because if we can start with, if we want to find, for example, a wall where paths are divisible by 6, then first we can find one where paths are divisible by 3, then remove them, like suppress vertices so that we have a simpler wall, and then apply argument for p equal 2. So this implies that whenever we have some m of the form 2 to the power of alpha times m prime, where m prime is odd, then this bound we have is polynomial in m times n times log to the power alpha of n. So here this power of log, this is not iterated log, this is power of logarithm. So this follows from the fact that we need to apply this bound alpha times, and we also have those p components which comes from odd factors in factorization of m, and we also have constant which come from this O, big O here and big O here, and they multiply, but only in the number equal to the number of prime factors of m. So they only contribute polynomial in m. So yeah, in particular, this implies that when we consider this Erdős-Pasha property with divisibility constraints, then we obtain a bound which is polynomial kn times some factor which is logarithm of kn to the power log m. And this is much better than the one which was considered by Thomason, because he gave some very simple argument which gives exponential bound, and it was much worse. But I think that this problem is in itself quite interesting, and we'll see why. I mean, there are some interesting parts in it. So let me first start with this observation that when we are dealing with walls, those are basically subgraphs of a hexagonal grid. You can see in this drawing of the hexagonal grid that this is a subgraph of a graph obtained exactly as the wall. And another thing that we would like to do is that instead of considering subdivisions, we would like to consider our graph Wn, so this unsubdivided wall, and assign weights to our edges. So we consider only like those labelings where each edge is assigned a remainder modulo p, which is the length of the path modulo p. So for the rest of the talk, I would like to give an argument, give a sketch of the proof for those two cases, the odd case and the even and the case where p is equal to. And yeah, we'll start with the odd case. And in some sense, odd case is much simpler than the case where p equals 2. And as you can see from the fact that we have a better bound for odd p. This is because we can do a very simple thing in the proof of the odd case. Namely, what we can do is that we can just split our initial wall. So we start with a large wall of size where side is roughly n times p. So we want to show that if we have a wall of size n times p, then we can find a n subwall with all paths divisible by p. So we can just start from splitting our wall into triangles which form a wall-like shapes. You can see that the graph of adjacency of those triangles is exactly the wall Wn. And we will show that in each of those triangles we can find a nice branch vertex, a good branch vertex, in such a way that we will be able to connect consecutive triangles, the branches vertices in consecutive triangles, so that the path will be divisible by p. So there are two possible cases. In the first case is that when there are a lot of zero edges, so there are a lot of edges with weight 0. if in our triangle we can find a vertex such that if you consider three edges emanating, three paths emanating from it, like on the picture. So one is going east, one is going southwest, and one is going northwest. Then, and you can find a vertex such that all vertices on those, sorry, all edges on those three paths are assigned a weight equals 0. Then we pick this as our branch vertex. So yeah, this is one case where we have a lot of 0 edges. We find a vertex like this.
So these paths go to the boundary of the triangle? Or?
No, they are vertices of, each of them is of length roughly 4p, and but they do not touch the boundary. They're somewhere in the middle.
Inside. Okay.
Inside, yeah. Imagine that your triangle is 100 times p, and in the center triangle of size 10p, you want to find something like this. So one option is that you find the structure, then you pick this as a vertex, this as your branch vertex for this triangle. And in the case where we cannot find such a tripod, this means that there are a lot of non-zero edges. Basically, wherever you put your black vertex, you will know that you will see nearby non-zero edge. So yeah, this roughly means that there are non-zero edges everywhere, and in particular, it means that we can find many non-zero edges which are far away from each other. And in such case, we would like to take as our xv vertex just in the middle of the triangle, and find a path which goes from xv to the middle of the side of a triangle, such that it visits many flowers, where a flower is a small hexagonal grid like this, where in the inner cycle we can find an edge with a non-zero weight. So clearly, since we have a lot of non-zero edges, yes, we can find a path which jumps from a flower to another flower and so on, and finally visits yi, which is the middle of a side. And we have those paths of flowers for all sides of the triangle. Yes, and those flowers will be useful because the fact that we have a non-zero edge here will give us some choice. It will mean that we will have at least two possible ways to go from the vertex where we enter a flower and the vertex where we exit the flower. So let us study those paths of flowers a bit more. So consider one such flower and a vertex S where we enter it and the vertex T where we quit it. So if all paths in the flower from S to T has the same weight, so that on any path from S to T, the sum of weights of the edges modulo P is the same, then we claim that E1 is equal to 0. So this will actually mean that all of the edges are equal to 0, but we will just prove it for E1, and it will imply that all of them are 0. By contraposition, this will mean that we will have at least two different weights, two different weights on paths from S to T. So why is that? Well, we can consider paths from ST which differ only on the inner circle. So for example, we can consider a path which visits vertices, which visits edges E1 to E5. So it goes, for example, here, 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 then goes on the cycle. No, sorry, I did it wrong. Here, 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 here. Or we can consider another cycle where those paths consisting of the edges E1 to E5 instead uses the weight E6. And since we are working under assumption that all paths have the same weight, we conclude that the sum of those weights is equal to this weight. And by a similar argument, we can see that the sum of weights of E1 and E6 is equal to the weight of E2, is equal to the sum of weights from E2 to E5. So now, if we add those two equations, we conclude that what we have here, we have twice weight of E1, then we have all those edges that are here from 2 to 5, and we have 6. So on the left-hand side, we have 2 times the weight of E1 and all remaining weights. And on the right-hand side, we have sum of weights from E2 to E5 and E6. So we conclude that this left-hand side equals right-hand side. So if we cancel out the repeated terms, we are left with 2 times weight of E1 equals 0. But we are working in the case where P is odd, so this implies that E1 indeed has 0 weight, has weight 0. So this shows that whenever we have a flower like this, and E1 is a non-zero edge, then we can find paths from S to T within that flower, such that they have different weights. And now this gives us a way to actually achieve any sum. So if we have a path of flowers, then the fact that at each place we can switch between two remainders modulo P implies that we actually can obtain any possible remainder modulo P. This is due to a theorem by Cauchy and Davenport, who showed that if you have some subsets of ZP, then the Minkowski size of those sets has size at least this term right here. But before we go into details what's on the right hand side, let us discuss this Minkowski sum. So Minkowski sum of some sets of ZP is the set of all possible numbers which we can obtain as a sum of elements where the first element belongs to A1, second to A2, and the last one to AM. And the set of, we denote the set of all such sums by A1 plus 2 blah 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 plus 2 AM. So Cauchy Davenport says that the size of such a set is lower bounded by the minimum of P and 1 plus sum of size of a set minus 1. So in our case, we would like our AIs to be the possible weights of ST path in the corresponding flowers. So we will know that each of those sets will contain at least 2 remainders modulo P. So this will imply that the Minkowski sum of those sets will be lower bounded by a minimum of P and here. But what we have here, our M is P minus 1. And each of the sets AI has at least 2 elements. So we conclude that 1 plus P minus 1 is equal to P. So we will conclude that this set of all possible sums will be of size at least P. Since we are a subset of ZP, this means that all possible remainders are reachable. Okay, so now, yeah, so this implies that a path of P minus 1 flowers contains X, V, YI paths of all possible weights. So recall that this YI is the vertex in the middle of the ith side of the triangle. So now we will show how to connect branch vertices using the branch vertices we chose. So
can we stop for a moment?
Yes.
So those tripods were of length P?
4P.
So then you need P flowers on the way. So why don't you need P square size of the triangle?
Okay, so I guess I'll need some Blackboard. There is one thing which I didn't explain in detail. So yeah, we have a white Blackboard. So when I said that when we don't have a tripod of so when I said that we have edges everywhere, I didn't like say exactly how I imply that, but exactly what you can assume is that you don't only consider disjoint tripods, but you consider all possible positions of tripods, and they will intersect a lot. And since if you will do some analysis and see that each edge belongs to a number of tripods linear in P, you'll see that actually the number of non-zero edges will be omega of P. So if you choose your side of triangle appropriately, you will have 4P, sorry, P minus 1 edges or times 3, which are far away from each other. Okay, so now back to the connecting branch vertices. So for each pair of consecutive triangles, we need to somehow connect branch vertices. And on each side, we either have a path of flowers or we have a tripod. So if we have 2 path of flowers, then it's easy because we can just choose the first path arbitrarily within the path of flowers. And on the other, just adjust the paths within the flowers so that the total weight is 0 mod P. Similarly, if we have a tripod on one side and path of flowers on the other side, it also works nicely because we can still just adjust whatever happens on the left-hand side so that it keeps a remainder 0 modulo P. So it remains to consider the case where we have 2 tripods. In such case, we would like to find 2P minus 1 disjoint paths from one arm of the tripod XU and one path from the arm of the tripod of XV. So given how they were constructed, we can easily ensure that we can find such linkages between arms and that they don't interact with each other or with those paths that we had in the earlier case. So now in such a linkage, we would like to choose a subset of paths which we will visit on our way from XU to XV. So what we need is that the number of paths we choose is odd because we need to go back and forth odd numbers of times so that we end on the right side, and that their sum is 0 modulo P, because recall that all vertices on the all orange edges have weight 0, so they do not contribute to the weight of the path from XU to XV. And this is a place where another theorem comes handy, the theorem by Erdős, Ginsburg, and Zib, which says that for any, if you have 2P minus 1 reminders modulo P, then you can choose a subset of P of them such that their sum is 0. So since we are working in the case where P is odd, this will in particular imply that such a choice of indices, subset of paths, will be good. So yeah, this completes the proof of the odd case. Now to the even case. So the only even prime is P equal 2. And this is more difficult. There is more, I think, more going on. It's not that we'll just things turn out them like, oh, well, let me just tell you what's the plan for the proof. So we start with a large wall. So it will be of size roughly n log n. And from this, we will first obtain a bipartite wall, which is only a factor of we only lose a constant factor on the size. So we start with a wall of size n log n, and we end up with a wall which is bipartite and is n log n. And then from that, we will contain an even n wall. For simplicity, I will call a wall where each path between 2 branch vertices is of even length. I will call such a wall an even wall. So here, by a bipartite wall, I mean that this graph is bipartite. This implies that the set of branch vertices can be partitioned into two sets, such that whenever you have a path between those two sets, then it has odd length, and if it's between two branch vertices which are in the same set, it will have even length. Yes. So
can you please comment on what breaks the previous group for P2, because it's going to be different.
So the main thing which we had in the odd case was that when we had this thing that when you considered what are the possible weights on the paths from S to T, then you knew that if all paths from S to T have the same weight, then it means that you have zeros everywhere. And this is completely not the case in here. You can have you can basically choose any bipartition of the vertex set. Sorry, you can, if you start with a wall like unsubdivided and partition the vertices into two sets, then you can construct a bipartite wall where the vertices from one set are on one side and on the other are on the other side, right? So this in particular implies that you I'll maybe draw on the whiteboard. So if you have your wall, bipartite wall, and say this is, you have red, and here you have blue. Then when you want to find your large even wall, then you know that all branch vertices will be here or all branch vertices will be here. So in particular, you fail at the very first step. You cannot do this trick that you partition your wall into triangles and pick one branch vertex in each of them. So there is a lot going on. For example, there's this result which says that if in a wall you have all cycles divisible by m, where m is odd, then this is equivalent to saying that the distance between any two branch vertices is divisible by m. So this with odd we have a lot more. There's a less thing that can happen, and in the case p equal 2, it's somehow that doesn't work this way.
So technically, you use twice the assumption on once over there with the flowers, and the second time at those Z, right?
Yes.
Looks
Avoidable.
It looks avoidable. Avoidable. So yeah, we start. So let capital N denote some omega n log n value, and consider any labeling of edges with the elements of Z2. So we have 0 and 1, which denote the parity of the corresponding path in the wall. So in our first step, we want to find a large wall which of size linear in n, which is bipartite. So we start from choosing a subgraph of our wall Wn, which has this property that every cycle has weight 0. So this is some equivalent of saying that we consider we would like to consider a subgraph of Wn such that the corresponding subgraph of the wall is bipartite, right? If we're dealing with this edge labeling, this is the equivalence of bipartiteness. So we want to consider the bipartite subgraph of Wn, which has as many edges as possible. And this property implies that we can find the two coloring of the vertex set of H, such that we have such that the weight of an edge xy is 1 if and only if the endpoints have different colors. This is pretty intuitive. So in our graph H, the following edges are allowed. So we have an edge bit of weight 1 between two vertices of different colors, a weight of, or an edge of weight 0 between two vertices of the same color. H is this graph we choose. So we want.
It's a subgraph, not reduced.
No, it's a subgraph. It's a subgraph which has this property that as described. So we want to find the largest, in some sense, bipartite subgraph of our wall. Okay, and in fact, since we want to have a graph H with as many edges as possible, this implies that this graph H is determined by a bipartition of or the two coloring of the graph Wn, because basically we can choose color vertices red and blue and take all edges which have this property. So this will be this is an equivalent way of looking at the graph H. So now we have two possible cases. The first case is that we can find many disjoint paths from top to bottom and many disjoint paths from left to right, where many is n/2. And this is easy case because if we have something like this, then what we obtain is n by 2 times n by 2 grid, which has this property that it's a subgraph of H, and therefore it corresponds to a bipartite wall. So we are, in this case, we are good. I mean, we need to be a bit careful with how those paths interact. It's that there needs to be there may be a need to do some cleaning up because those paths don't have to go such nicely, but it's pretty intuitive that if we have something like this, then there's a lot of crossing. We have n by 2 times n by 2 bipartite grid as a minor, and then we can obtain a wall by taking a bit larger n. So now we are left with a case where we don't have many paths from top to bottom or bottom or left to right. So by some Menger theorem or some Max-Flow min-cut theorem, we can deduce that this implies that there exists a small set of edges which separate top from bottom or left to right. So why I say so by Menger theorem, we know that there exists a small set of vertices, but since we are dealing with a wall, we have a maximum degree 3, so the vertex disjointness and path and edge disjointness are equivalent. So we can assume that we have a small set of edges which contains less than n/2 edges, which separates without loss of generality top from bottom. So here is an example of a graph. The black edges is our graph H. We have some two vertices, so that after removing them, our graph splits into two parts, V1 and V2. So we define V1 as the union of all components of H minus F, which contain at least one vertex from top, and V2 is all remaining paths, all remaining vertices. So let us first observe that in our original wall, we had at least n paths between V1 and V2. This is because if you consider the n disjoint paths from top to bottom, then each of those needs to contain at least one which goes across between V1 and V2. So we can see that here, 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 here. There must be at least n of them. And by our assumption, we have F consists of less than n/2 edges. And therefore, we can flip the edges which are present in H and those which are not present in H across V1. And we will preserve bipartiteness and increase the number of edges, which will contradict our assumption that we chose H with the maximum number of edges. So if you look at the colors on the boundary of like what happens between V1 and V2, then if we flip the colors in V2, then it will also flip which edges between V1 and V2 are present or not, right? So if we flip colors on the bottom, then this flips the edges. And since this set F has less than n half, this means that we improved, and we chose H with maximum number of edges, which means that the proof is complete. So what we just showed is that whenever we have a large wall which is of size n, we can find a subwall of size at least linear in n, such that it's bipartite. So this means that now we are dealing with this case where we have a wall where the branch vertices are of two colors, and all it remains to show is that you can find a large subwall where all branch vertices will be of the same color. And this is where it's pretty difficult, because it seems intuitively it seems that if you have two coloring of a wall, you should be able to find a wall of roughly the same size which has vertices of one color, but it's really hard to capture, and this is where this n log n comes from, because we didn't find a way to construct a linear to show that there always exists a monochromatic wall of linear size. So right here we are now dealing with the case where we are going from bipartite n wall to an even n wall. So we will try to use divide and conquer approach. We will have a recursive procedure where we split our wall into smaller parts, do something inside, and then combine results to get something bigger. So the most naive approach would be just split the wall into 4 parts, and in each of them find a large monochromatic wall recursively. And this works, right? We can do it this way, that we find, for example, some walls from each part we get a red or blue monochromatic wall, and then combine 2 of them which have the same color. But this won't give us anything good, because we are very wasteful. Out of 4 parts, we only use 2. And you can see that this is very bad. For example, if you know that if all 4 subworlds use roughly the same amount of red and blue, then we will have large walls of both colors, but we will always use only 2 of them. So this is not very good. We need to try to somehow improve it. So another attempt is that we should try to, in our recursive procedure, to obtain two walls, one of one color and the second of the other color, so that the total size is large, and then combine them. But now the problem is that if we don't control the shape of the graph, which we get from the recursive call, then it might be very difficult to combine those components into our wall we want to obtain, or whatever we want to obtain. So now we can try something very ambitious and say that maybe we can do that. We can find, for each subwall, we can find some parameters n1 and n2, which have a total large sum, and have this property that whenever you want to obtain any subgraph of a grid of size n1, you can get it. And whenever you want to obtain a red subgraph of a wall of size n2, you can get it. So we would like to we would like our recursive calls to return us some two values n1 and n2, such that whenever I want some graph of size n1, I get it, and whenever I want whenever I want a blue graph of size n1, I get it, and whenever I want a red graph of size n2, I can get it. And this is also wrong. This is a bit too strong. Now we need to weaker this a bit, because if we would like to have any graphs, then this might be difficult for us to connect them, and it's not obvious whether we can split any graph. So for example, if you want to combine it to construct a graph of size where sizes are n1 prime, n1 double prime, n1 triple prime, and n1 quadruple prime, so the sum of those n's, we should split our graph into size of into graphs of these sizes and somehow connect them. And it's not really clear if we can do that. Maybe it's possible, but what we did is a bit different approach. Namely, we modified this this approach where we don't get arbitrary subgraphs of a wall, but only one of a special form which can be nicely cut into pieces which can be connected. So this is a construction which derives from the Hilbert's construction of a space-filling curve. So we can define a Hamiltonian path pk in the 2 to the power of k times 2 to the times k grid as follows. So we start with P0, it's a 1 by 1 grid, so it's a single vertex. Then P1 goes right bottom, right down left. And then if you want to obtain a pk plus 1, you split your grid into 4 subgrids of size 2 times smaller, and go like shoop, 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 and shoop. And so you have, this way you obtain a Hamiltonian path between 2 consecutive corners in your grid. And this is really, this construction has some very nice properties. For instance, if you enumerate all vertices on such a path, pk, there are 4 to the power of k of them. And if you look at the graph induced by the consecutive subgraph of the grid induced by the consecutive vertices of your graph, then, well, if you choose I as some value divisible by 4 to the power of alpha, so you take 4 to the power of alpha consecutive vertices such that the first vertex has index divisible by 4 to the power of alpha, then you obtain a square grid of size 2 to the alpha times 2 to the alpha, right? So you, for example, see that the first pair vertices induce a 2 by 2 grid, then following 4 also, and so on. And this has important consequence. Namely, if you have some subgraph induced by vertices from I to j, then there are roughly square root of j minus I vertices which go from that subgraph to the outside of the grid. Why is that? Well, you can, if you look at this subset, the part from I to j, then you can split it into into those grids of size 4 to the alpha, and each of them will have only a number of edges going outside, which is linear in the side of the grid. And since we will have at most, we will have constant size of each grid size in the optimal partition of of the subgraph into grids. This will imply that the total number of outgoing edges will be like square root in the number of vertices in this subpath. So here's some example. So for example, if here we have some Hilbert path and we consider a subpath which looks like this. The corresponding graph G2K looks like this, and the green parts represent the attachments to the outside world. And as I mentioned earlier, the number of them is linear in the number of edges in this subgraph. From this, we can move on to the walls. So if you remember the construction of the wall, we had this property. This was constructed in such a way that on each path, you consider if you consider every horizontal path and partition it into parts of 2 consecutive vertices, then you obtain a grid after contracting them. So this means that for each vertex in the grid, there's a corresponding pair of vertices in our wall, unsubdivided. And therefore, this graph G2Kij gives rise to a subgraph of the wall W2Kij, which looks like this. And finally, we define a graph W2K plus Ij, which is obtained from this graph, from this subgraph of the wall, by attaching an edge to each place where it has some contact with the outside world. And now, in our recursive construction, we will be finding some subdivisions of W2K plus Ij, with this property that all those vertices which are black here are of one color in our prescribed coloring of the edges of vertices, and the attachments are on the boundary of the outer face. So now, this is our procedure. So we recursively call to, we have a recursive call to 4 subwalls. From each of them, maybe what is the thing that we're interested in? So let's define T of n as the smallest n, such that for every 2 coloring of Wn, there exists lambda1 and lambda2, such that the sum of lambda1 and lambda2 is n squared. And for each I, there exists a blue subdivision of this subgraph W plus of size lambda1, so that it's attached to the outer face. And there will be also a red subdivision of lambda plus of size lambda2, which is attached to the outer face. And now I claim that this value T of n satisfies this recursion. So we have T of n is at most 2 times T of n over 2 plus O of n, which, as we well know, means that T of n is O of n log n. So the proof of this is just we need to look at this recursive procedure. So for whenever we call some subwall with our procedure, what is returned is some values lambda1 and lambda2, such that we can obtain a red subdivision of size lambda1 and a blue the subdivision of size lambda2, where the subdivision is of graph of this form, W plus. So if you want to achieve this, we consider 4 subwalls of size T of n over 2, and leave in between them some space, which is linear in n. Now, for each of them, we can obtain by induction some lambda1 and lambda2. And our lambda1 and lambda2 will be the sum of the corresponding lambda1s and lambda2s. It's right to see that whenever we have something like this, we can actually obtain a red subdivision of size lambda1 and blue subdivision of size lambda2. So let's look at the red subdivision. So if we have lambda, we want to obtain some subdivision of size lambda1, so a graph of this form, then we can split it into subgraphs of size lambda1, like the lambda1s we got from the recursive calls to the subwalls. and say that we would like to subgraphs of this size, the corresponding subgraphs, with attachments to the outer face. And now we know that between any pair of those vertices, there is only the number of edges in between is of order square root of lambda 1, which means that the O of n space in between suffices to connect them as we wish. This is a bit hand wavy, but I think that this is gives you some idea of how it works. If you'd like to make it more rigorous, you can first just consider 2 consecutive and just merge them into a one graph, then the other 2, and then the combined, like the sums of 2 can be summed into sum 4. Yes, and this shows that actually it suffices to start with a wall of size n log n. And that's the idea of the proof. Thank you.